Hello everyone, good morning. I'm Sai Kumar Sirangi and my teammates Karthik Reddy Mankonda. Today we will be explaining how deep learning and large language models have transformed natural language processing or NLP. The ability of machines to understand and generate human language has revolutionized industries like healthcare, finance, customer service, and more. In this session, we will cover key NLP concepts, the evolution of NLP, deep learning fundamentals, large language models, and their applications. Let's dive in. What is NLP? NLP is a fascinating field that combines artificial intelligence, linguistics, and computer science to enable machines to understand and process human language. It powers everyday applications like virtual assistants, for example Alexa and Siri, and machine translation, for example Google Translate, chatbots, sentiment analysis, and more. The core challenge is that human language is complex, full of ambiguity, slang, and different structures. The evolution of NLP, especially with deep learning, has made machines much better at handling these complexities. Coming to the next slide, what is NLP tasks? Coming to NLP tasks, NLP is used in a wide range of applications. Some key tasks include text classification like spam detection, where emails are categorized as spam or not. Machine translation allows automatic translation of text from one language to another. Speech recognition and synthesis enable voice assistants to understand and respond. Sentiment analysis determines whether a statement is positive, negative, or neutral. Named entity recognition identify names, places, and organizations. Other tasks like test summarization, question answering, and topic modeling are essential in automating information processing. Coming to the history of NLP Part 1. NLP has come a long way. It started with rule-based systems where language processing was based on hand-coded rules. The 1950 Turing test suggested that language understanding is a key measure of intelligence. In 1954, the Georgetown IBM experiment performed one of the earliest machine translations. The 1980s saw a shift towards statistical models, and in 1997, LSTMs helped solve long-term dependencies in tests. Today, deep learning, especially transformed Bayesian models, has revolutionized NLP, enabling the creation of large language models like GPT and BERT. Coming to the next slide, history of NLP Part 2. As we know that in 1997, LSTMs have solved long-term dependencies in tests. Today, deep learning, especially transformer-based models, has revolution in NLP, and for example, creation of large language models like GPT and BERT. Coming to the next slide, introduction to deep learning. Deep learning is at the art of modern NLP. It uses neural networks with multiple layers to automatically extract meaningful features from raw text data. The key enablers of deep learning include powerful GPUs that speed up computation, optimized algorithms like Adam and Dropout, and the availability of massive datasets. These elements allow deep learning models to learn complex patterns in language. Coming to the next slide, deep learning versus traditional machine learning. Traditional machine learning relies on manually engineered features and simpler algorithms, whereas deep learning leverages neural networks to automatically extract patterns from raw data. This shift has led to significant breakthroughs, particularly in NLP, where deep learning models can capture contextual meaning better than traditional methods. Coming to the next slide, neural network fundamentals. Neural networks are the foundation of deep learning. They consist of layers that transform input text into meaningful outputs. During training, the model performs a forward pass to compute predictions and a backward pass to update its parameters using gradient descent. This optimization process ensures the model continuously improves its ability to understand language. Coming to the next slide. Key deep learning components. Deep learning relies on several critical components. Residual connections help deep networks train efficiently. Distributed training with multiple GPUs speed up computations. Mixed precision training improves memory efficiency. Curriculum learning allows models to learn progressively from simpler to more complex tasks. Transfer learning enables fine tuning of pre-trained models, saving time and resources. My friend will continue from the next slide.
Hi everyone, my name is Karthik. Now we are discussing about training deep model effectively. Efficient training is crucial for deep learning. Techniques like batch size tuning and learning rate scheduling help improve convergence. Early stopping prevents overfitting by monitoring validation loss. Gradient clipping helps in stabilizing training for RNNs and LSTMs. Hyperparameter optimization using grid search or Bayesian methods ensures optimal model performing. So moving on to the next slide. Recurrent neural networks, which is known as RNNs. RNNs are usefully for sequential data like text. They process words one at a time while maintaining memory of previous words. The architecture, often used in mechanic translation, consists of an encoder that compresses input and decoder that generates output. However, RNNs struggle with long-term dependencies, leading to development of better architectures like performers. So in the next slide, we are discussing about the attention mechanism of this. The attention mechanism, which is introduced in 2014, allows models to focus on the most important words in a sentence. Instead of treating all words equally, it dynamically assigns different importance levels. There are various types of attention, including encoder decoder attention used in translation and self attention used in transformers. This advancement significantly improves NLP performance. Here we are discussing about the transformer architecture. The game changer in NLP was the transformer model, introduced by Vaswani et al. In 2017. Unlike RNNs, transformers use self-attention mechanisms to process entire sentences simultaneously, making them more efficient. They include multi-head attention, positional encoding, and layer normalization. This architecture forms the backbone of modern NLP models like GPT, BERT, and T5. So here we are discussing about the large language models, which is known as LLMs. LLMs are powerful deep learning models trained on vast amount of text data. Traditional models like ngrams and HMMs were limited, while RNNs and LSTMs improved sequence modeling. However, transformer based models like GPT and BERT revolutionized NLP by enabling better contextual understanding. Today's LLMs like GPT-4 and Gemini can handle multimodal inputs, making them even more powerful. So in the next slide, we are discussing about the LLM training and life cycle. In training, LLMs involve several stages. First, they undergo pre-training on large text corpora to learn general language structures. Then fine-tuning adapts them to specific tasks. Reinforcement learning with human feedback aligns models with human intent. Deploying these models requires large-scale parallel computing using GPUs and TPUs, as well as techniques like model and parallelism. Here we are discussing about the modern techniques in LLMs. Several advancements improve LLM performance. So LoRa enables efficient fine-tuning. Quantization and pruning reduce model size for faster inference. Mixture of experts activities only parts of the model for efficiency. Retrieval augmented generation. Combine search with text generation. Finally, prompt engineering helps guide model responses for better accuracy and control. Next, Applications, challenges, and solutions. LLMs have numerous applications including chatbox, education, legal, and medical text analysis, and content summarization. However, they face challenges like high training costs, hallucination biases, and data privacy concerns. Solutions include foundational models like OpenAI's GPT, retrieval augmented generation, and reinforcement learning with human feedback. So, in the conclusion of the future of NLP and large language models, as we wrap up, let's conflict on the key takeaways from today's discussion. NLP has evolved from simple rule based methods to complex deep learning architectures, transforming how machines understand and generate human language. The rise of transformers, particularly models like BERT, GPT, and Gemini, has set new benchmarks for AI driven text processing. However, as these models grow in power, they also bring significant challenges. Training large language models requires extensive computational resources, making them expensive and energy intensive. Moreover, biases in training data can lead to biased outputs, and ensuring ethical AI development remains a progressing concern. Despite all these challenges, ongoing research is addressing these limitations. Techniques like LoRa, which is known as low rank adaptation, make model fine tuning more efficient, while quantization and pruning reduce computational cost. Retrieval augmented generation, which is known as RAG, improves functional accuracy by integrating real time information from external databases, and mixture of experts enhances model efficiency by activating only relevant portions of the network of each task. Looking ahead, LLMs are becoming more multimodal, meaning they will not only understand and generate text but also interpret images, videos, and even real time interactions. They are also improving in real world applications such as personalized education, AI powered healthcare assistances, and automated legal document analysis. In summary, NLP is an exciting crossroads. As technology advances, we must balance performance with responsibility, ensuring that AI systems are efficient, ethical, and aligned with human needs. Future of NLP is not The future of NLP is not just about building bigger models, but about making them smarter, safer, and more accessible. Now, my friend Sai Kumar going to explain about the future outcomes of NLP and large language models.
As we look toward the future of NLP and large language models, several exciting developments are on the horizon. The field is evolving rapidly, and we can expect significant advancements in the following areas: more efficient and cost effective models. The current generation of LLMs requires massive amounts of computational power and data. However, future models will prioritize efficiency through techniques like LoRa, model quantization, and mixture of experts, which will make training and deployment more cost effective. We may also see lightweight and domain specific LLMs that are fine tuned for specific industries, reducing unnecessary computational overhead. Coming to the next part, enhanced accuracy and reduced bias. One of the biggest challenges with LLMs today is hallucination, where models generate incorrect or misleading information. Retrieval augmented generation will continue to improve factual accuracy by integrating real time knowledge sources. Additionally, ethical AI research will drive the development of bias mitigation techniques, ensuring fairer and more transparent NLP models. Multimodal capabilities. The future of NLP is not just about text, it's about integrating multiple data types. We are moving towards multimodal AI, where models can process and generate text, images, audio, and even video simultaneously. This advancement will lead to more intuitive virtual assistants, AI powered content creators, and even real time languages translation with visual context. Personalization and adaptability. Future NLP models will be more personalized to individual users. AI will adapt based on user preferences, communication styles, and specific needs. This will revolutionize fields like education, customer service, and content recommendation where AI can tailor interactions to individual users in real time. Coming to the real world applications and industry disruption, LLMs will continue to transform industries by automating and enhancing various workflows. Some anticipated applications include healthcare, legal and finance, education, creative industries. Coming to the healthcare, AI powered medical assistants that help doctors with diagnosis and research. Legal and finance, automated contract analysis and fraud detection powered by LLMs. Education, AI tutors that provide personalized learning experience based on a student's strengths and weakness. Creative industries, AI generated art, music, and literature blending human creativity with machine intelligence. Thank you for your time, and I look forward to your questions.